Hi everyone. Again, my name is Jyotinder, and today I'll be talking about practical quantization in Keras and how it can help you run large models on smaller devices. So again, as I think I've already been introduced, I work on ML frameworks at Google, and my main focus here is working on Keras and Keras Hub. So neural networks are expensive. They are expensive to run, and they are expensive to train. They're expensive to train because models nowadays have hundreds of thousands of parameters in each of their layers. And every time that you do a forward pass or a backward pass, that model has to perform hundreds of thousands of high precision floating point operations. And floating point operations are expensive. Our regular hardware, like CPUs, are not super optimized to perform these many floating point operations at the same time or parallelly. So we need to use expensive accelerators in the form of GPUs and TPUs to make these models run and train efficiently. Now, this hardware is not just expensive, it's also scarce. The best hardware out there is already booked out and sold out for like the next 5 years. And it's already been bought up by the big players. The computational cost is also pretty high because all of this hardware requires lots of power, and because of that, it also requires lots of cooling. So that adds to both the power costs as well as the infrastructure costs for the cooling required for that hardware. Now, as the models grow in size, they of course grow in their storage footprints as well. So where our machine learning models used to span a couple of gigabytes, they have gone up and blown up into several hundred gigabytes to a few terabytes now. And all of these things come together and make it way harder for us to run all of these models on the edge. Now, by edge, I mean embedded devices like your smart glasses, your smartwatches, your smartphones. And I also mean running these LLMs locally on something like your personal computer or your MacBook or any laptop that you might have. Because there you do not have data center grade cooling, you do not have data center grade hardware. So how do you run these models on these devices, and how do you run them well? And to drive the point home, I have a graph here where I have the growth of the size of the top open source LLMs over the last 4 or 5 years plotted against the size of the VRAM modules on the top data center grade chips from that year. So you see that we've gone from having LLMs which were a few gigabytes in size up to somewhere in the several hundred gigabytes range. And this is just for the open source LLMs. In fact, if you look at the proprietary closed source models, they're already in the couple trillion parameter range pretty comfortably. So these numbers would just blow up there. And the data center grade hardware, we went from the A100 a couple of years ago, from around 2021, I think, which had the VRAM of around 80 gigabytes, to the B200 today, which has a VRAM of 192 gigabytes. So you see that the VRAM has comfortably lagged behind the size, the growth in size for these models, which also means that you can't really run these models on a single chip anymore, not at least the larger versions of those models. And if you come down to the consumer GPUs, the ones which people like you and me can buy, like the NVIDIA RTX series, like the 3090 and the 5090s, the growth in the memory modules is even more limited, and it's been constrained down to like 24 to 32 gigabytes. So if you have a great local model, something like Quencoder, it's super hard to run that on your own machine, and at least run that well with very low latency that you require when you are coding or writing some code, right? So how do we solve this? So quantization is one of those ways which is super effective in reducing not only the power draw of your models, but also in reducing the latency. The main idea here is that the weights of your models, which are stored in high precision floating point numbers, you reduce the precision of these floating point 32-bit numbers or 16-bit numbers down to some lower precision fixed point format, something like an 8-bit integer, or even lower sometimes, which is like 4-bit integers. And the benefit that you get here is that a lot of the accelerators that you use, such as GPUs or TPUs, they have hardware and they have kernels which are optimized for performing these matrix operations on these low precision operands, right? And there's like two main categories of how you do this entire technique. It's like post-training quantization and quantization-aware training. I'll mainly focus on PTQ for this presentation in the interest of time. So let's go a little bit deeper. So when you have tensors that are stored in 32 bits, and you go down to something like 8 bits, the most immediate benefit that you see here is that your storage overhead decreases by a factor of 4, which is pretty easy to see. And the computational cost also reduces quadratically by a factor of 16. How do we get 16 or the quadratic decrease? If you multiply two 32-bit numbers, you get a 1024-bit result. And if you multiply two 8-bit numbers, you get a 64-bit result, which is a 16 times decrease, right? And the benefit that you get here, and the fun part about performing quantization on neural networks, is that most neural network architectures out there are pretty resilient to the reduction in the precision of your weights. So what happens is that the hit that you get on your accuracy is also pretty minimal. And you're able to get away with pretty good numbers in terms of accuracy when using these techniques, right? But again, nothing comes without trade-offs. And if you move to lower and lower bit widths, the compression increases. Longer acceptable. So to drive this point around how quantization actually helps, I think it will be helpful if we understand how the hardware actually works and how you actually perform matrix multipliers and matrix operations on these neural network accelerators, right? So here I have a schematic of how a simple matrix vector multiply happens on a neural network accelerator, something like a TPU, or something like a GPU, right? So a matrix vector multiply can be understood of as a very simple building block for bigger matrix multiplies, or even convolution operations that you use in your neural networks today, right? So this hardware block aims to sort of parallelize as much computation as it can to make sure that whatever matrix operations you're doing, they're happening efficiently, both in terms of power and both in terms of latencies, right? So this accelerator is made up of two main units. One of them is the processing element, which is represented by C here in the 16 grid array, which is a 4x4 grid, and the accumulators, which are represented by the letter A on the right-hand side in the red boxes. So when you start a matrix multiply, a matrix vector multiply, the first thing that you do here is you load up the accumulators with the value of the bias that you add to the result. Once the accumulators are loaded up with the bias, you load up the arrays here with the values of the weights and the inputs of your matrix W and your vector X, right? So you load up the weights W into the arrays on the left-hand side and the vector X on the array on the top. And each of these processing elements in the 4x4 grid, they perform a multiply of their respective elements. So if you look at C11, it's supposed to multiply X1 with W11 and so on as you move through the array. And once all of these elements have performed their respective multiplication, of all the processing elements in that row, right? Now, when you're training your neural network, this training happens in 32-bit floating point numbers. the forward pass happens in 32-bit and the backward pass happens in 32-bit, because it helps, the 32-bit floating point numbers help represent the gradients very well, and the gradients flow very well, and you're able to converge pretty well. If your inference hardware, the hardware that you use when you're just deploying the model and when you're running the model, if that's supposed to support these 32-bit operations, it needs to have the same 32-bit hardware, which is more expensive and which has higher latencies as well. And these MAC operations and the data transfer to and from the arrays into the memory is what usually consumes the bulk of the energy that you spent during neural network inference. It also consumes the bulk of the latencies that you spend, latencies that you incur when you are performing this inference. So if you move down to lower bit widths, something like int8 or int4, you can get a lot of benefits here in the form of not only reduced data transfer, but also in the form of latencies that you incur when you're running any kind of inference. The less data transfer and the cheaper operations in terms of the hardware that you use also reduces the power draw as well as the cooling that you need to have in place to make these things run well. So how do we actually move from this high precision 32-bit floating point into a low precision representation? There needs to be a certain scheme which allows us to move between these two regimes, right? And the intuition here for the same is that any floating point vector, let's say represented by x, it can be approximated as a scalar value, a high precision 32-bit scalar value multiplied by a vector of integer values. So on the screen on the right here, you'll see that I've defined x hat as an approximation of the original vector x. And this approximation can be computed by multiplying a high precision scalar number with a vector, with an integer vector. So if we replace the operands in the original vector matrix multiply equation from the previous slide, with these approximations, we get the equation that you see here. And if we expand the representations of w hat and x hat in this equation, we get the multiplication between these scalar numbers as well as the integer vectors. And now the interesting thing here is that the scalar factors that we have, sw and sx, respectively for your weights matrix as well as the inputs vector, these factors are multiplied with the entire tensor that you have, the entire integer tensor, and it does not really depend on the summation here. So we can actually take those out of the summation. And what you see here is that we are performing a pure integer-integer multiplication inside the summation, and now we're able to make use of integer hardware for performing these matrix operations here. And that result that you get from these operations can simply be scaled up using the scalar factors here. And then you later add on the bias to it. And you'll notice that we do not actually approximate the bias in the same manner, because biases tend to be way more sensitive to the quantization noise. And if you actually end up quantizing that, you might see way larger quantization errors in the final results of your computations. And this scheme, if you try to formalize it, is called the uniform affine quantization. And it's the most commonly used quantization scheme out there. And you mainly require three kinds of parameters for this quantization scheme to work. The parameters being the scale factor, the 0 point, and the bit width b. Now the bit width is what defines how large the integer range would be where you're able to map your floating point numbers into. So this bit width could be 8 for int 8, could be 4 for int 4, and so on. And the scale factor and the 0 points are what define how you actually perform this mapping between the integer realm and the floating point realm, right? And it's pretty easy to actually perform this conversion. This might look pretty complicated, but it's super easy, trust me. So you have an integer grid that you define based on the bit width. So you have the bit width here. So if the bit width is something like 8, you will go from 0 to 2 to the power 8 minus 1. This is the representative range of the integer number line that you have. So if this was 8 bits, you would go from 0 to 255 here, right? Then you perform the actual conversion from the real or the floating point vector to the actual integer vector. So how do you do that is, the scale factor that you use, you divide your real or the floating point valued vector by the scale factor, and you get a particular value. And then you round it to the nearest integer. Once you round it to the nearest integer, you already have an integer value, and then you add the 0 point to it. So you add the quantization factor z into the result that you get after the rounding operation, and then you just clamp the result that you have between the representable range that you defined right here. So if in case the value of this computation actually falls outside of the representable range of your integer number line, you just clamp it there. This clamp operation is usually available as like the clip operation. So you might know it as the clip operation if you've done some machine learning before. And to go back from the integer representation back to the floating point representation, you just do the opposite of what you just did in the first equation there. You simply subtract the 0 point from the integer representation and multiply it with the scaling factor. And that's pretty much it. That's all you need to know to actually perform quantization. Now, how do you actually compute the scaling factor? It's also a pretty simple and intuitive thing to actually understand. So if you have a tensor with the maximum value, let's say 125, and you have a integer representation where the maximum representable range is something like, let's say, 16, you want the maximum value that your tensor requires to the maximum value that is represented by the number line. So you just divide the two. So you divide 125 by 16, and that's your scaling factor. That's a pretty simplified way to look at it. You have to account for a couple of other things when you're actually implementing it, but that's pretty much the gist here. And to simplify things and to, in fact, make certain computations even more efficient, we can just say that the 0 point is equal to 0. We can map the 0 in the real or the floating point range to the integer 0 in the integer range, and we get a much more simplified equation right here. And what we get is, to convert from the floating point values to the integer values, we just divide our real value with the scaling factor, and we just clip the values between the representable range, right? And we just do the opposite again to actually go back. And this actually helps with performance as well. There are certain operations which can be performed way, way more efficiently if we do not have to deal with like an addition factor of the 0 point when going through the forward or the backward pass. So let's take an example to actually understand what's going on. So if we have a vector x, let's say 0.2 and minus 0.5 on the left, and we have a vector w, 0.3 and 0.8, and we have arbitrary scaling factors with them. So the scaling factors can be 0.1 and 0.05. The first thing that we want to do is we want to quantize this real or the floating point number into the integer range. So it's pretty simple. We round the result of the division with the scaling factor. So we divide x by sx, and we round it to the nearest integer. And we perform division of w with sw, which is the scaling factor for w, and we round it to the nearest integer again. And we get the resultant vectors here. Second, we perform the integer accumulation, or the, in simple terms, just the multiplication between these two vectors. So if you multiply them, the result that you get is minus 68. And again, one cool thing here that you'll notice is that we are again only performing integer multiplication here, and there is no floating point operations happening. We are multiplying 6 with 2, we are multiplying 16 with minus 5, and then we are adding the integer results from both these multiplications into another integer result. And finally, if we want to go back to the floating point domain, let's say into another layer which does not support quantization, all you need to do is simply do the reverse of what you just did in step 1. You divided your vectors with the scaling factors, you just multiply it now, and you get back the original dequantized result, which is minus 0.34. So the result that you see here would have been the same result if you actually multiplied the original vectors x and w together. But the benefit of this approach is that you actually have to perform 0 floating point multiplications when you're in the quantized domain. And going back to the schematic simplifies in a way, in terms of the hardware components that you use, that now the arrays that you use, the systolic arrays here, only need to handle integer operations. So you have int8 values representing your input values and the int8 values representing your weight values. And you perform the multiply accumulate operation and you accumulate a 32-bit integer result. The reason it's a 32-bit integer result is that when you multiply two 8-bit integers, you get a 16-bit integer. And when you add enough 16-bit integers, you can get a 32-bit result. So that's why you sort of get a 32-bit accumulated result. Now, when you have to send it back to the memory, you can optionally quantize it again into int8 so that the amount of data that you transfer also reduces. So this also sort of helps with the efficiency part of the story here. And now let's talk about post-training quantization, on how you actually perform quantization after the fact when you have already trained a given model. So if you are using a pre-trained model from any model garden out there, and you want to perform quantization on it, the easiest way to do it is PTQ, which is post-training quantization. So the post-training quantization methods are usually data-free. You don't require access to any kind of training data here. And there are ways where you can require a small calibration set in exchange for better accuracy. So these can be data-free, or these can sometimes require a calibration set. And they usually require no hyperparameter tuning here, because it's usually just as simple as just a single API call. So it's pretty intuitive, pretty easy to actually use. So the workflow you'd usually use here is either train a full precision model or get a full precision trained model from some model garden, something like maybe the transformers library or Keras hub. Then in case you're using a calibration-based quantization technique, you can collect a small calibration set, which is sort of representative of the kind of data that your model will see in practice. Then you quantize the weights and activations, and this quantization could use the calibration data that you might have collected, or it can be data-free again, as I mentioned previously. And once you're done, you can run quantization inference directly on it. But again, one thing to note here would be that you would only see benefits from quantization in terms of latencies if the machines that you're using to run this model actually support this low precision fixed point hardware. The thing about this is that if you run something on, let's say, an older MacBook, it might not have the right neural processing units or the tensor processing units to actually perform the low precision fixed point matrix operations. But usually if you have a modern enough graphics card or something like a modern enough TPU, it will have the required hardware and you would see the benefits there. Now coming to Keras. Keras is a deep learning API designed for humans. If you have done any kind of deep learning, you might already know about Keras. And Keras 3 is a multi-backend framework, which means that you can use the same modeling API with any backend that you like. You can use JAX, TensorFlow, or PyTorch on the backend while using the same API on the front end to build your model. So this allows you to actually move seamlessly across these different backends to leverage the strengths of each of these frameworks. So if you train a model in JAX, because JAX works super well with TPUs on, let's say, GCP, you can then deploy this model that you've trained in JAX on TensorFlow without really any kind of specific tuning that you need to do when using something else. So there are a lot of deployment options and deployment frameworks out there which work super well with TensorFlow. And if you're moving to a more modern library like JAX, it's pretty easy to actually use the existing deployment infrastructure, because you can simply move across these frameworks without having to change anything else about the model. And the Keras ecosystem consists of several libraries, but the two major ones that we actually work on right now are Keras Hub and Keras RS. So Keras Hub is very similar to something that you might already use. It's a pre-trained modeling library which provides the Keras implementations of most popular model architectures. Something like if you're looking for, let's say, the GPT OSS implementation, or you're looking for some other implementation, you would usually find it there. And then you have Keras RS, which is a recommenders library, which has the building blocks you require to build recommender systems on top of Keras 3. So it provides those building blocks in terms of layers and other infrastructure. which can actually help you create Keras-based multi-backend recommender systems. So how do you actually do quantization in Keras? Quantization is sort of exposed to the users in the form of a single unified quantize API. So this API can actually be called on top of both a model or a particular layer. And you pass the bit width or the technique that you want to quantize the model to. So you can pass something like int 8, or you can pass something like int 4 to quantize that particular layer or particular model down to the required bit width. So the cool part about the layer-specific API, which is in the second line here, is that you can have more exotic quantization schemes in your models. You can have certain layers which are more robust to quantization, quantized down to lower bit widths, like int 4, and you can have the other layers which might be a little bit more sensitive to the quantization noise, quantized to something like 8 bits. So it actually allows you to mix and match these different quantization bit widths. And Keras supports a couple of quantization modes, the two major ones being int 8 and int 4. Float 8 is not actually a quantization mode, but it's actually a mixed precision training and inference mode, which makes use of quantization internally to provide you hardware acceleration when you're actually training a neural network. So it's also a pretty interesting thing to check out. And then we have GPTQ, which stands for Generative Pre-Transformer Quantization. And it provides you with the benefits of high compression that int 4 or other lower bit width techniques provide. And it's able to retain most of the performance in terms of the accuracy numbers that you see. But again, it requires a small calibration set for getting that performance out. So the typical workflow that you would follow when you're using Keras Hub and Keras for quantization is that you would load your floating point model. You would calibrate it if required for that particular quantization mode. Something like GPTQ would require calibration. And the calibration actually happens automatically when you call the quantize API. And then you actually quantize the model weights after the calibration actually happens based on whatever bit width you actually want to quantize to. And you can actually run the model, or you can just save it for later use on some other hardware. So time for a live demo. Let me open the notebook that I have here. So the first thing that I do here is that I load the Gemma 3 model here. Gemma 3 is the state-of-the-art model from Google, which is available on Keras Hub. So the first thing I do is I import Gemma 3 causal LM from Keras Hub. And the second thing that I need to do is this will just provide me the implementation of that model in Keras. What I actually need to do is I need the actual weights for a particular preset to be loaded into this model. So in this case, since I'm running on a MacBook, I'll actually use a smaller model. I'll use the 1 billion parameter model here, and I'll load that into a Gemma 3 object. It won't take too long on my machine because I have the model cached locally. Next, I'll generate some text, and the generation API is pretty intuitive. You can just call .generate on the model, and it will generate some text here. So the first time that you run, it will actually compile a computation graph in whatever backend that you're using, and then it will actually perform the inference here. So the first time that you actually run it, it will usually take longer. The next run would actually be way more instantaneous. Now, the inference that you saw here actually happened in high precision in floating point FP32. Now, if you want to quantize it down, let's first quantize it down to 8-bit integer. Now, what happens now is that Keras traverses the entire model graph, and it finds all the layers that actually support 8-bit integer quantization. Every such layer that it actually finds, it quantizes its weights down to that given bit width, and then moves on to the next layer. Now, we can use the same generate API, the same one that we used with the full precision model, to generate a result. Now, since we quantize the weights, we will have to recompile the computation graph, so that recomputation will happen, and then once that is done, we'll get the output here. So we get the output, and you see that it's quite close to what the original output was, but it still has some differences. So you see that it has this additional thing that it says it's designed to be easy, which is sort of not there in the original one. So you actually know that there is a difference in the model weights now, which is allowing us to maybe run more efficiently, but the results are different. And you would see some level of drop in quality, might be very small, but it will be there because you are sort of adding some level of compression. Now, you could also do something like a more aggressive compression. So I would run this same notebook again, but this time we'll try to go for 4-bit quantization. So I'll load the backbone again. I'll load the causal LM model again with the same weights from the 1 billion model. I'll again generate the text, and I'll this time quantize it down to int4. Now, int4 quantization does a few extra things as compared to int8. Since most hardware like kernels actually support the lowest bit width the lowest addressable unit that they support is a byte, and 4 bits is actually half a byte. What you actually get is a model which is able to compress 2 weight values into a single byte. So this, when you call quantize with int4, you not only just quantize down to the 4-bit bit width, you actually pack these weights together to actually get the benefit from 4-bit quantization. So every single byte actually has 2 weight values packed inside it. And when you perform inference, those weight values actually need to be unpacked before we perform the matrix multiplier to perform the forward pass. So again, since we quantized this to 4 bits, the computational graphs were cleared out, and you actually compile the entire graph again, and then you produce the output. And it's very evident here that the result here is way lower quality than the original one with the high precision numbers, because the compression is so high. There's another reason that the result is not that good here, is that Keras currently uses a per channel quantization scheme. So every output channel gets its own scaling factor. But you can actually get better performance if you use something like sub-channel quantization, which we plan on adding later on. So sub-channel quantization allows you to have multiple scaling factors per output channel, which actually improves the performance, and you get way closer results to the int8 quantization here. But it's again, it offers these benefits at the cost of some level of performance and some level of storage trade-offs. And that's pretty much about the live demo here. Let's start back again from here. And how does quantization actually happen? I think I went over this very roughly when I was showing the live demo. So when you call quantize on a model, it traverses the model graph and tries to call quantize on every single layer that is there inside it. So if you have a dense layer, it will call quantize on that dense layer. And for the weights of that layer, it will try to determine the kernel scale. It will determine the scale and then quantize the weights of that kernel. It will update the D-type policies. The D-type policies refer to the data type information that we store in that particular layer. This policy information is actually used during serialization and deserialization so that you can actually restore these models correctly to their correct bit widths. And then you rewire the forward pass so that the forward pass now knows how to use these quantized kernels. And then you clear all the pre-compiled graph cache so that it can automatically recompile the next time that you run a forward pass here. And when you run the forward pass, you call the inputs on the model. You go through an internal quantized call API, which is sort of hidden from the user, and it goes into a hook that it calls on the dense layer. So these hooks that are there, such as the int8 call, allow you to do something super interesting. So if you have a custom layer that you've implemented in Keras, you can actually make it support quantization by implementing such a hook. We already provide these hooks for the most common layers out there, like the dense layer or the Einsum dense layer, which is the Einstein notation. And we already provide these int8 and int4 hooks for those layers. So it calls that particular hook, which knows how to perform the forward pass. And that hook, first of all, dynamically determines the quantization scale for your inputs. The reason you do that is you're trying to quantize both the weights, which are already quantized during the quantization operation, and you're trying to quantize the inputs as well using a dynamic scale based on the statistics that you get from the current input batch. So you actually quantize the inputs as well, and then you perform low precision fixed point multiplication between the inputs and the kernel. The kernel was, again, quantized previously during the quantize call. The inputs were just quantized during the forward pass, and then you perform the matrix multiplication with them. Now, in case the next layer actually took a high precision input, you would ideally dequantize the outputs right here to floating point 32. If it doesn't, usually the optimizer would abstract away and sort of remove the dequantize and quantize operations that might need to happen between the two layers. So if the optimizer notices that you dequantize the outputs here, and they go into the next layer, and they need to be quantized again, it would usually just remove that entire part and give you that benefit of not having to do that quantize, dequantize operation. And let's look at some performance benchmarks. So I have some benchmarks here for the 4-bit quantization. And on the left-hand side, we have Distill-BERT model trained on the SST2 dataset. And you see pretty significant reduction in the model size as well as the peak memory used. And you even see benefits in terms of the latencies and the throughput, while having a very, very minimal change in the accuracy of just 0.92 percentage points. If you try to quantize a large language model such as Falcon 1B or sometimes even Gemma 3B, which might be trained on a particular data set, you will see bigger accuracy losses here. So you see that there is a perplexity increase of more than 34% when using the int4 quantization scheme. Perplexity sort of represents the confusion that the model faces when predicting the next word. So you have an increase from 7.44 to 9.98. Again, this is mainly because we use per channel quantization in Keras for now. But you do see that wherever you can actually bear this kind of increase in perplexity, you do get something back in terms of the performance. So you see that the model size decreases quite drastically. The peak GPU memory decreases by 30%, which makes it easier to run this on smaller consumer-grade chips. And you also see benefits in terms of the latencies and the throughput here. So the numbers that you get back are pretty impressive as well. But what if you do not want to actually deal with such high accuracy losses? So we have a technique that we support called GPTQ. It's based on the GPTQ paper which is available out there. So it's a weight-only quantization technique where you don't actually quantize the inputs and you only quantize the weights of the model. And you actually perform sort of like, you compute a Hessian proxy of the weights matrices so that you know how each weight's value and output actually interacts with the other weights in the weight matrix. And you perform a column by column quantization. And once you quantize one column, you try to see that the quantization error that is now present in that particular column, how that actually affects the rest of the values inside the weights matrix. And you try to sort of offset that by changing the rest of the values in the matrix. And that's how you actually perform this calibration-based method. So you have a calibration data set that you provide in a config. You provide the tokenizer that you want to use to sort of tokenize the inputs here. You tell the model, you tell the framework the bit width you want to quantize to. In this case, you're quantizing down to 4 bits. The group size is basically how big the groups for each of your scaling factor would be. Like in this case, if I have 128, every 128, you can say weight values will share one quantization factor. So that refers to one 0 point and one scale factor. The number of samples you want to use and a few other things. Now you call model.quantize with the argument GPTQ, and you pass the config that you just created to the same API. And if you look at the performance numbers, you see that the perplexity decreases are way smaller. The perplexity increases actually become just 1%, 10%, 7%, and 3%, which is way more acceptable, while still retaining the disk reduction and VRAM reduction benefits here. But since this is a more sophisticated technique in this sense, and it does not actually quantize the inputs, you're not able to benefit from those 8-bit multiplies. So you actually have to perform sometimes multiplies in something like FP16. So you don't see as dramatic decreases in the latencies or as dramatic increases in the throughput. And that's pretty much it for my talk. And I would want you guys to probably try out Keras and Keras Hub. And if you find something interesting, and I hope you guys actually build some cool stuff out of it. And that's pretty much it for my talk.
We'll take questions. Let me also apologize. I realized we kicked this off a bit early, so we got an extra 5 minutes or so of the talk, and we have a little bit more time for questions than we would otherwise. But apologies if you missed the start of the session because I launched things a little bit early. Yes.
Hi, so I wanted to ask, so I'm trying to get more into machine learning and deep learning. I've taken classes on it and I really enjoyed it. And I see a big difference between applied machine learning, which is taking existing models and using them with data sets, and things like this, which I think are really interesting, but are more theoretical. For the second side, the more theoretical side of things, where would you recommend to get started, and what do you think companies care about more? Do you think that big companies care more about the low-level implementation design or your understanding of the high-level application?
I think it depends on the roles that you're applying to. If you want to get into core ML, which sort of this part actually covers, we call it core ML at our company. It's always helpful to have experience implementing things, implementing papers from scratch. So if you actually contribute a lot of these open source libraries that a lot of these companies support. So Google supports Keras, Meta supports PyTorch. Those are really good ways to show some level of proof of work, that you know how the library's internals work, you know how the internals work. You just don't have the knowledge of how to use a library, but you actually can contribute there. You know about the performance characteristics of different kernels, and you actually have the aptitude to sort of implement something from scratch by just looking at maybe like a reference paper or something like that. I think that's valuable. Other than that, I think it's more about practice as well. I think you can read as many papers as you want, and you can implement as many models as you wish to, but there is some bit of tinkering that is always important. Trying to tinker things outside of what's already in the spec, right? So if you have, let's say, if you're implementing let's say a quantization scheme like the one I talked about in the paper, and you try out some different things, like what if, right now Keras is doing per channel quantization, what if I try to implement something like a sub-channel quantization scheme or something like that? That will definitely lead to way more, I think, learning in terms of you tinkering around with the framework, you learning about the nitty-gritties of how matrix multiplies are actually happening, how you can make them more efficient. Like one of the learnings that I had while actually implementing one of these techniques here was that I implemented the entire technique, but it turns out that in the computation graph, there was no low precision multiplication happening, and I was still multiplying 32-bit numbers, even though I felt like I was doing everything right. So going deeper into that, trying to debug those small issues that come up here and there because of maybe something that you missed, I think that's where most of the learning actually happens. And I think building proof of work is probably the most important way to actually show the hiring managers that, okay, I know what I'm talking about. And proof of work is the easiest thing to show if you have something like an open source contribution.
Hey, so when you kind of rewrote the MAC operation, you mentioned that bias is much more sensitive to quantization.
Yeah.
And if you imagine like a module with like a linear layer and then like a ReLU or something like that, you're going to need to like dequantize your activation before like adding bias and then like passing it through your ReLU.
Right.
So my question is, what's the overhead of these kind of like quantizing and dequantizing operations in the architecture, and are there like alternative schemes to get around doing that as many times in your forward pass?
Yeah. There's actually tricks there that you can use. I've not explored them too deeply, but actually the paper that I've linked in multiple slides at the bottom here, the paper is by Qualcomm called a white paper on neural network quantization. It's a really good paper. I think everyone should read it if you're getting into quantization. It talks about some of these schemes where you can actually avoid doing like those quantize, dequantize operations. You can sort of fuse certain operations. Sometimes you're able to fuse a ReLU with like a bias add or something like that. So the way you would probably do it is instead of the ReLU being from something like maybe, I'm going off the top of my head of what I remember, so it might be slightly inaccurate, but instead of, let's say, you clamping the value at 0, you clamp it at the bias value, and you don't really have to actually perform like an addition there. And there are like several such techniques. So I would really recommend you guys to check out that paper. It goes really, really deep into a lot of these optimization techniques. And in terms of like the performance itself, like performance in terms of accuracy as well, if you want to get better numbers, there are ways to not just round to the nearest integer, rounding up or rounding down. There's techniques called add around as well. So following those techniques, you'll get better numbers too. So there are like so many things that you can do. So I think it's a great thing to actually explore.
What's the name of that paper again?
A white paper on neural network quantization. That's the name of the paper. It's by Qualcomm. It's pretty famous. I think when I was learning, like that's where I started off. I think that's it. Okay.
If you don't mind a small bit more time. With the fast integer multiplication versus floating point operations, where is where is the slowdown in floating point operations? Is it implementing a technically correct, like IEEE correct floating point operation? Is it like handling that exponent? Why is integer faster?
Yeah, that's actually pretty accurate what you just said. So you have to sort of shift the exponents around to sort of align them between the two operands. You have to ensure that there's no overflows that are happening. And generally, when implementing floating point in hardware, it just is more steps compared to a single fixed point operation. So the hardware is more complicated, and it has more steps to it. So you have to sort of align the exponents, you have to perform rounding off, and then you have to sort of, I think once you get the result, you have to sort of put the alignments back to where they were. I think there's quite a few things that happen there. There's rounding happens, there's corrections that happen to ensure that you don't get garbage results sometimes, which happens in floating point operations, which is what actually takes away the time.
And when you're calculating a scaling factor in these based on some sample, is the limit of calculating the scaling factor for each value somewhat like equivalent to doing a floating point operation? I guess what I'm saying is, does the performance value come from only looking at the exponent a few times? So
the interesting part here is that you only do this during like when you're actually quantizing, and you do this just once. You quantize the weights just once, and you incur that, let's say, whatever small computation cost might be there, you incur that cost just once during the quantization operation. You never have to do that again when you're actually running inference, which is what you care about.
Right.
Yeah.
Thank you.
Yeah.
All right, well, let's thank our speaker one more time.